Alright, so exponential functions actually have a lot of practical uses. One of the more common ones is looking at interest rates and how that's going to affect the value of an initial amount. We also use it in studying populations, whether it's of cities or maybe it's bacterial cultures. They can grow exponentially as well. Now, the first thing we're going to look at are exponential growth and decay formulas. Now, if a value is increasing over time, we're going to have an exponential growth problem. If something is decreasing in value over time, it will be an exponential decay. So growth or decay, depending on whether something is increasing or decreasing. Now, both of these are a function of time, which means the value you get is dependent on how much time has passed. Most of the time we're dealing with years, but it can be other values. So, for instance, if it's a bacterial culture, it might happen over the course of minutes. So it just depends on the scenario. Now, in both of these formulas, A is the initial amount. How much did you begin with? R is your growth or decay rate. Now, it's going to give it to you as a percent, but you need to input it to the formula as a decimal. So, for instance, let's say we had a 3.5% increase. You would want to plug in 0.035 for R. Or maybe it's a 0.8% increase or decrease. It would be 0.008 as a decimal. So just be careful about your rate. And then, of course, T is your time. So let's look at some examples. In this example, it says you invest $1,800 in an account that increases by 7% each year. Now, the first thing we're doing is we're writing a model to represent this scenario. It's a function of time. Our initial amount is $1,800. Our growth rate, because it is increasing, it's growing, so we're adding here, by 7% each year. But remember that you must make that a decimal. So 0.07 to the T power. That's our model. And we can use this model to figure out the amount after a certain amount of time. So, for instance, if I wanted to know how much would be in the account after 15 years, I would plug in 15 for T. Now notice here I went ahead and added 1 and 0.07. You can do that. You can even put it here as as 1.07, and it'd be correct. So I just made up some of these numbers, so I don't know what they're going to come out to be. So let's see, 1.07 to the 15th power. So we're dealing with money, and remember, money has 2 decimal places, so we're going to have to round 4,000. Actually, let's not put the comma. $4,966.26. Remember, you got to round. Okay. So another example. A brand new car costs $28,900. It depreciates in value 7.6% each year. Now, depreciate means its value is going down. So we're going to use an exponential decay for this one. The model for it we start with A, which is the initial amount, $28,900, and then 1 minus our decay rate as a decimal. So you move your decimal to left to get 0.076 to the T power. Now, to figure out the value after 3 years, what we're going to do is plug in 3 as my exponent. So 28,900 times 1 minus 0.076 to the third power. And this gives me a value of $22,798.89. All right, one more example with growth or decay. Now, in the year 2000, a town, I changed it from a city to a town because that was not big enough. A town had a population of 10,903 people. This population increased 2.3% each year. So the model to represent this, it's an exponential growth because it's increasing in value. The growth rate is 2.3%, so 0.023 here to the t power. Now the population in 2019 is what I ask for next. So keep in mind that you're not going to plug in 2019 as your time. We're going from year 2000 to year 2019. That's a time interval of 19 years. So just be careful if they give you the time in a different way. So 10,903 times 1.023 to the 19th power means the population increased to 16,795 people. Now I am not putting a decimal here because you can't have just part of a person, so we round to the nearest whole number. Now another application of exponential functions is with compound interest. Compound interest is when we look at interest not just on the initial amount but also how much interest has been paid into it already. Now A is the total amount in the account, it's your balance. P is called the principal, which is the amount you first put into it. N is the number of times a year the interest is compounded. R is still your percent written as a decimal, and T of course is still your time in years. So a savings account pays 0.8% interest bi-monthly. So this tells me R, this tells me N. Bi-monthly means twice a month. Since there's 12 months, we do 12 times 2 to get 24. We invest $300 into the account. Now the model for this, again, this is basically plugging everything in but T. So principal and then 1 plus point, oh my goodness, I wrote down the formula wrong. Shame on me. This should be R, this should be N. I did not catch that earlier. This is why you proofread, children. Alright, so the rate goes on top, sorry about that, over N, the number of times compounded. That's 24. And then my exponent, well, that's N times T, so 24T. This is the model we're going to be using to express the amount in the account at the end of a certain time period. So if I want to know the amount in the account after 10 years, what I'm going to do is plug in a 10 for T. So 300 times 1 plus 0.008 over 24 raised to the 24 times 10 power, or 240. So the amount in the account after 10 years is $324.98. Now the total amount and the interest earned are not the same value. If I wanted to know just how much interest was earned, I would take the answer I got here, the total amount, and subtract from that the amount you first put into it. So the interest earned for this problem over the course of 10 years would have been $24.98. Okay. Let's do one more problem like that, and then I want to talk about a couple other phrases you might see when talking about what your end value is. But first, this one. Let's say you take out a loan for $25,000 to buy a car at 4.5% interest, which is compounded monthly. So the model we would use to represent this, we plug in 25,000 for P, and then you have 1 plus the interest rate. You have to write it as a decimal, so 0.045. Compounded monthly means it's compounded 12 times a year. And then n times t, so 12 times t is your exponent. Now, you can often choose how many years you want to take to pay off a loan. And it's usually better if you try to pay it off sooner so you don't pay quite as much interest. And I'll show you what I mean in a moment. So let's say if we took 5 years to pay off the loan, what you would do is you would plug in 5 for t. So 25,000 times 1 plus 0.045 divided by 12 raised to the 60th power, because that's what 12 times 5 is, means we're paying a total amount of $31,294.90, because the 9 rounds up to a 10, so that makes the 8 go up. Now, just to show you, this is the total amount you would be paying back in 5 years, but if you took a longer amount of time, let's say 6 years, you'd be paying back more money. So just a little tip, if possible, try to pay it off sooner, because you're not paying as much interest. You might have larger monthly payments, but in the end, you're actually paying less. Alright, back to this problem though. The amount of interest paid after 5 years, to get that value, we take the total amount paid and subtract from that the initial amount borrowed. Excuse me. To get $6,294.90. Alright, now just a couple of other phrases. If you're trying to figure out how many times a year it's been compounded, you might see phrases like weekly, which tells you n is 52 because there's 52 weeks in a year. You might see the word quarterly, that's 4 times a year. Annually means once a year, or semi-annually means twice a year. There can be other phrases, but these are some of the ones that you're going to see on my assignments more often. Alright. That's it for this one.